and that includes kinetics or chemical kinetics that we've just finished, and these are all primarily in terms of rate laws. Now we're getting into chemical equilibrium. And this is referred to as extent of reaction. And we will get to, after studying the chapters on equilibrium, which include this chapter and 3 more after this in specialty topics. And we'll get into chemical thermodynamics. And this deals with determining the feasibility of a process. Will it work or will it not work? So, putting things in perspective, we are, of course, right here. To understand how chemical equilibrium relates to chemical kinetics, we'll start with a graph I've drawn a number of times. It talks about the concentration changes in reactants as a function of time. Where we have reactants going to products, we start out with 100% reactants, and we go to a certain amount of product. Well, when the reaction, before the reaction starts, how much product is generated? None. I mean, it's just, think about it for a second, it's a logical deduction. So, and I will ask you to consider a reaction in that context in working problems in chemical equilibrium. I tell students to think of the reaction before it starts as horses in a track, at a racetrack, in a cage, waiting to cage to open, and then the horses run. Well, that's the way I want you to think in terms of the and you'll see why later on when we build what we call the ICE table. Anyway, starting with 100% reactants in the starting gate, so to speak, then we open the gate and let the horses run. Well, when the reaction starts, the horse is running, we have a decrease, logically, in the reactants, and we find this trend. And then the products, of course, are made from the reactants, and they will increase, and we see a general trend as shown here, like this. Well, this can be divided into 2 parts. This, from this point where we start at 0 time to wherever, time-wise, from here to this line is called the kinetic region. And it is the kinetic region and applies to the rate laws that we've studied, concentration, rate averaging, coefficients, and decay curves, and what have you. In this portion of the curve, no tangent is constant. So you have a constantly changing tangent in both the reactant concentrations and the product concentrations, and it's decreasing to a 0 tangent. zero slope. At that point, we begin the equilibrium region. No mystery, you've seen this before. And it continues. Now, you'll notice that the concentrations do not appear to undergo change, and that's one characteristic of equilibrium. The values of the concentrations reach a point at which there is no apparent change in concentration. However, the reaction is continuing and is called a dynamic equilibrium. Get this up here. And in a dynamic equilibrium, we have reactions moving forward at the same rate as a reaction moving in reverse. One illustration that I use is a container of water. And once the water's added to the container, molecules begin to evaporate under the standard conditions. And if we put a top on that cover on the container, then there's a point at which the area or region above the liquid becomes saturated with gas molecules of the liquid. And when that happens, the molecules in the liquid continue to go into the gas phase, but at the same time, molecules return to the liquid phase. And one is a forward reaction, one is a reverse reaction. And in this case, we would write H2O liquid in equilibrium with H2O as a gas. And this is the forward, and this is the reverse of that reaction. And this begins our study of the chemistry of equilibrium. Now, in analyzing this from a stoichiometric standpoint, this is based upon the law of mass action. Very important little starting point to understand how the concepts of equilibrium evolve out of kinetics, and we'll see how that works right now. So as the reaction enters into the equilibrium region, the rate forward is equal to the rate in reverse, and that simply is the law of mass action. So the law of mass action states and the rate of reaction in the forward direction is equal to the rate of reaction in reverse direction. And this is the foundation that evolves into the concepts and applications of math to the equilibrium concepts. And this is written in this form: the rate, reaction forward is equal to rate, reaction in reverse. And let's assume, say you're given reactants going to products. Reactants A going to products, whatever they are, decomposition or whatever. Now, we learned that in order to write a rate law, we always write it in terms of the reactant side. And we come in and we write rate equals K, bracket, molar concentration of whatever the reactants are, raised to the X power, like that. And that's what we learned in the kinetics region. And so what we'll do is, say, assign this one as, say, the forward reaction, and we'll put an F on that K and call it the forward reaction, and write the second. When the reaction goes back in the other direction, we put another arrow. This is forward, and this one is reverse. Rate reverse. I should have written forward up here. Reverse is equal to K reverse R times the concentration of A, still using reverse products, excuse me, those are the reactants that are going back in there. Products raised to the, say, Y power, whatever they are. Like that. Now, applying these two reactions to the statement of the law of mass action, what would we do? We'd say the rate forward equals the rate in reverse and equate these two expressions. We can say K forward times the concentration of A, which is the reactants left to right, raised to the X power, would be equal to K in reverse times the concentration of products. I can make that look like a reverse of products raised to the Y power, like that. So this should be reasonably familiar to you based on what we've already covered. So when I give you an equation and ask you to write the rate law of it, you should know rate equals product of concentrations of the reactants raised to whatever order of reaction we would determine experimentally. Like in the T-butyl chloride, the order of reaction came out to be 1 based on the analysis from the experiment. Well, what this is supposed to tell us is the extent of reaction. Which is a measure of the equilibrium nature of the reaction. How long does it take to get to the equilibrium part of the curve? So what I want to show you here is the same concentration time curve, and some reactions have broad extents of reaction. So the distance between the starting point and the point at which the reaction enters the equilibrium region is essentially extent of reaction. Well, this is, say, reaction 1. Well, a different reaction may have a very short extent of reaction in that it reaches equilibrium very quickly, such that we start at, say, 100% reactants, but we see a trend like this, and the reaction, I'm going to separate them because they're different reactions essentially. So we're talking about extent of reaction 2 being between the red lines here. Between here. Well, what I'm asking you to do, or what is typically done in defining extent of reaction in terms of the expression up here, is we need a rate constant ratio and concentration ratio that as the reaction produces more products to reach the extent of reaction, one that has a large extent of reaction, we want it to come out a large number. That's the essence of what I'm trying to get to here. How do you manipulate this expression to get a large number? And that will be related to the equation. You'll see more detail of it after this is the basis of it. Anyway, so I want to take this expression and solve it for a rate constant ratio equals some concentration ratio, such that as more products are produced, we get bigger numbers. That's the idea. So, okay, let's start here. That's the law of mass action. Rate forward equals rate in reverse. Now you have two options here. You'll have K forward over K reverse as one option. And so that would be concentration of products raised to the Y power over reactants raised to the X power. Or you would have the inverse of this, which would simply be K reverse over K forward is equal to concentration of reactants raised to the X over products raised to the Y power. So let's see which one gives us an increasing ratio. Okay, if we run some experiments. So this is a hypothetical reactants going to products. Okay, in case 1, we're going to bigger numbers from reactant concentrations to product concentrations. So I'm going to say this one is 1 mole or something like that, and it's going to 10 moles. Okay, so that's experiment number 1, or reaction 1. I can change that to reaction number 1. And we want to compare that one with a different kind of reaction that starts with a large amount of reactant and winds up at equilibrium with just delivering small amounts of product. That is, what if we started with 10 moles of reactant and we wound up with it only delivered 1 mole when it reaches that equilibrium region? That would be a different reaction, number 2, like that. Well, how do the K value ratios, respond in this? Okay. So if we have a large amount of product, and let's assume a first order reaction, X and Y are 1. Order of reaction. So those are first powers over here. So I want this K forward over K reverse gives me a concentration of products, which is 10, divided by the concentration of reactants. See that? 1. In reaction number 2, the products are very small. Okay, it starts out with 1 divided by reactants, 10. Okay, this is this consideration right here. Now, this one, the second one over here, starts out with reactants over products. And so that would translate to reactants are 1 over 10. And this number would be 10 over 1. So jot that down and let me explain what I'm trying to show you. What we're looking for is a ratio. You'll choose one of these. One will not be used, one will. That when you apply the equilibrium concentrations to it, reactions that give you lots of product and leave you with very little reactant will be big numbers. But those that do not deliver large amounts of product will give you small numbers. And they're a reaction I'll show you in a few minutes. So if we look at the trend between, on the first reaction, here is reaction 1 that's going to larger concentrations. I'm giving you bigger numbers, right? And so this, if I increase numbers, I'm getting a 10. That's a big number because, see, it's producing more. But comparing this reaction to this reaction produces much less than the first reaction, but it gives you a small number. Okay? In the second consideration over here that we're looking for, what we're doing is characterizing a reaction. Every reaction has a number associated with it, every one, that defines how much product is produced or how much is not produced. That's what equilibrium is. So in this one, if we look at this one, in increasing concentrations from 1 to 10 gave me a small number. That's not what we want. We want increasing concentrations to give me big numbers. Here is a decreasing a small amount of yield giving a large number. That's not what the equilibrium analysis is supposed to show. Bigger numbers say this reaction produces a lot of product, fundamentally. Or small numbers say this reaction produces very little product once it reaches equilibrium, and everything else stays in reactant form before it starts going back and forth. So this consideration is X'd out because it doesn't show what we're trying to show. We need a number that increases for increasing yields or larger extents of reaction. A big number means a large extent of reaction. Small numbers mean it reached equilibrium very quickly and didn't deliver very much in it. And I'll show you the issue. Well, what this is referred to, this ratio, which is products over reactants, will in fact give you increasing numbers for increasing yields. We change this ratio into a K value, capital K value, called the equilibrium constant. So if I have K forward over K reverse, then I'm going to change that or redefine it. You don't need to know what the K values forward and reverse are. All you need to know is that you're working with that ratio, forward over reverse. And the K is called the equilibrium constant. And it's like a fingerprint. Every reactant has its own K value that defines how much product is generated or not generated. If we have small numbers, it means it reaches equilibrium quickly and very little product is generated. Or if we have reactions that have very large numbers, it means that you have very little concentration of reactants left over and everything goes to product. And that's what this whole concept of extent of reaction. So the K value is extent of reaction relative to the size of the number. That is, large K values give you large extent of reaction and large amounts of product at equilibrium. That's the essence of what we're trying to describe here. Small K values give you small extents of reaction and small amounts of product at equilibrium. And that's what it is describing. So this is your objective, is to come up with whatever this K value is, and it's called an equilibrium constant. And every reaction has its own personal equilibrium constant. Okay, I need. But here are two reactions with significantly different K values. Here is N2 plus O2 goes to 2NO as a gas. Its K value is 4.6 times 10 to the minus 31. Compare that with ethylene. Hydrogenation is the reaction, producing ethane. Look at its K value, 1.3 times 10 to the 21st. So this first reaction would have a very shallow extent of reaction. It would reach equilibrium almost instantly. Second one, complete conversion of the reactants to products. You probably wouldn't find any reactants after this reaction was completed. But here you would find most of the reactants still unreacted once it reaches the equilibrium point. The equilibrium constant does not have units to it. It only is important to the magnitude of the number, because the larger the number, it just simply says this reaction produces a lot of product or not produce a lot of product. And it has its value in comparing one reaction efficiency to the other. In applications of using the K value, the equilibrium constant is typically the EQ subscript is substituted with the type of essential reaction or system that it relates to. So you have a gas phase reaction or heterogeneous reaction with gas phase, then what they call this is a Kc value. And that means concentration terms in molar quantities. Most of what I'm giving you now is definitions and trying to put things in perspective. We hadn't worked the problem yet. So you'll understand what the terminologies mean. If you're working in, say, soluble weak electrolytes, liquid phase, you'll find the K values expressed as a variety of things. If you're working with acids in solution, the reaction is referred to as a Ka. Well, I'll bring that down here. If you're working with weak bases, you'll be working with KBs. If you're working with salt ions in poorly soluble salts, you'll be working with KSP numbers, called solubility product constants. This Ka is called an acid ionization constant. The Kb is called a base ionization constant. So I'm just giving you some definitions of how things are presented in this idea of studying equilibrium. You have some other terminologies which are KFs. That's a formation constant. So you're given a number that reflects its formation. When A and B come together, you have a number that says, okay, this does come together well or not. The size of the number is all you're interested in. Then you have a KD called a dissociation constant, and that happens to be, watch for quiz 1 over KF. It's the reciprocal, or vice versa. Kf is 1 over the dissociation constant. Now everything on the page here in this list are weak acids, and you'll notice over here the numbers vary, and there's a acetic acid 1.7 times 10 minus 5. It's a size factor. Now what I said earlier is their greatest value in K values is comparing reactions. If it's a big number, it yields more than one that has a smaller number. In the acid world, the bigger number means it's a stronger acid. It ionizes and delivers more hydronium ions into solution than a reaction has lower numbers. So as you look at this collection and you're interested in, say, acetic acid versus benzoic acid, who's the stronger acid? It's the one with a bigger K value. That's the primary objective here. Everybody okay on that? I mean, it's really straight up stuff, man. And then you can go down. Now, some of the reactions have 2 K values because you recall, what are the strong acids? One of them is H2SO4 to the first ionization step. You know, and we talked about ionization step, first ionization, second, and then phosphoric acid has 3 ionization steps. Well, each ionization step has its own K value because it's an individual reaction. And so if we're talking about carbonic acid, look at the size of carbonic acid. It's a 10 to the minus 7 number versus a 10 to the minus 11th. What does that say about the ionization of HCO3? Well, it's not as efficient as the first ionization step. So, I mean, that's what your interpretation should see when you are drawing conclusions about strength of acid between two comparative reactions. We'll be working with Kb values, the same issue. Now, these are listed as ammonias and ammonia derivatives called amines, A-M-I-N-E-S. Amines, you show aniline, dimethylamines, ethylamines, all these. When you put them into water, they coordinate with water and make an ammonium hydroxide or aniline hydroxide, anilinium hydroxide is what it's called, or dimethylaminium hydroxide. And so I'll show you that when we start working with them formally. But the numbers and efficiency of dissociation of the hydroxide is over there on the right. That's the base ionization and breaks up into the cation and anion. And so who's the stronger base? Well, it's the bigger number. Like that. Look at some of these. There you go. If I can get it on the page there. Wait a minute, let me see. Yeah, I can get that on there. There's ammonium hydroxide. You drop that in water and it has ionization potential of 4.6 times 10 to the minus 33. Barium chromate. It has a 10 to the minus 10. Very small numbers. But the barium chromate is a bigger number and therefore delivers more ions into solution. That's what the K values are telling you. And so as we go through these chapters, the K value is interpreted as a number, the extent of reaction. That's what I mean. The extent of reaction of the barium chromate in this is greater than the extent of reaction of aluminum hydroxide. So those are the fundamentals that we need to understand as we get into the equilibrium analysis. Okay, writing equilibrium expressions, equilibrium constant expressions. Plan ahead. We can't read that last word, it's expressions. So the first step in working equilibrium type problems, of course, to write the reaction you're interested in, the object of interest is, say we have 2H2 as a gas plus O2 as a gas and equilibrium with 2H2O as a gas. So it's all gas phase. So that would be, we'll be working with a Kc value. The relationship that we determined a few minutes ago was K forward over K reverse is redefined as a K equilibrium constant. Since everything's gas phase, that would represent a Kc expression. And when we wrote the expression, it was products raised to the, say, y value, thank you, and reactants raised to the x value. So this is the order of entry into the expression. This is the equilibrium expression. or equilibrium equation for the reaction that you're interested in. So if I want to write a Kc expression for this reaction, I would set it equal to products over reactants raised to the appropriate orders of reaction. Now, listen to me on this. In the kinetic region, the exponents or orders of reaction had to be defined experimentally because you have a constant changing in slope, right? Okay. In this one, the coefficients are the orders of reaction. You can use them because their concentrations don't change and you have a constant slope. That is, products raised to the, in this case, y over whatever they, and these are coefficients of the balanced standard equation. You remember the standard equation is the equation written so that the coefficients are in the smallest whole number ratio. And so that would represent the standard equation given its conditions of 0 degrees Celsius and 1 atmosphere. So if I use this format to write the expression for this equation, I would write Kc equals to the molar concentration of products is what I want to work with. And that was only one H2O liquid raised to the second power, because that's the coefficient, divided by the molar concentration of hydrogen raised to the second power times the molar concentration of oxygen raised to the first power. And you don't have to put a 1 up there if you don't want to. Everybody knows if it's 0, it goes to 1 anyway. But if it's a 1, it's understood to be that. This is the equilibrium expression, mathematical expression, for this reaction. And it defines the equilibrium concentration values. So the values you put in here would represent the extent of reaction values determined by some instrumental method or whatever. And we will cover that in due time. Or the problem will give you concentration values. Now, remember, these concentrations are molar. When you have these little brackets on there, moles per liter. Now, problems will come to you with moles also. And you cannot calculate a K value from moles. You have to convert it to moles per liter by dividing by whatever the reaction chamber volume is. And we'll get to that. But I just want to emphasize that the values in there will be molar numbers, 0.023 molar solution, whatever. Heterogeneous reactions are mixtures of solids, liquids, and gases in this case. Only the gas phase components are entered into the reaction equation, the equilibrium expression. because the gas phase are the only thing that affects the extent of reaction. Solids and liquids don't, and we'll get to that in due time. But suffice it to say, if you have a reaction, as I'm about to give you, say graphite carbon plus CO2 gas, and an equilibrium with carbon monoxide gas, what is the expression for that? Well, you would not put the molar concentration of carbon in there, just the gas phase. So your Kc expression is products, molar concentration of the carbon monoxide divided by the molar concentration of CO2, raised to the first power, because it balances with ones, like that. So this is just a little insert in there, but it is valid in that you use it. I'll give you another example. H2O as a gas condensing to H2O as a liquid, a condensation type reaction. Well, what's the K expression for this one? Well, it's a Kc expression, but you would not put this into the expression. So what do? The product is simply listed as a 1 divided by reactant concentrations like this. So only the gas concentration, the more gas you get into the region above the liquid, defines how the extent of that evaporation or condensation. Gas going to, yeah, that's condensation. But it's products over reactants, and that is the expression, so whatever this is. Okay, another Kc expression or equilibrium expression is partial pressures of the gases in a reaction. Equilibrium expressions in terms of partial pressures. According to Dalton's law of partial pressures, each gas in a mixture of gases has its own personal partial pressure. So if we have a reaction that's all gases, there are two ways, two equilibrium expressions that can be written here. It's all gas. There's one. So if I have CH3OH, which is methanol, in the gas phase in equilibrium with carbon monoxide in the gas phase and hydrogen in the gas phase, 2H2 gas. The two equilibrium expressions are one in terms of the molar concentration of the components, and two, what we call a partial pressure equilibrium constant. Well, the one that we covered is products over reactants, and that would be carbon monoxide gas, molar concentration raised to the first power, times H2 gas raised to the second power, and divided by CH3OH, methanol in the gas phase, raised to the first power. So that's one that is, you write in terms of molar concentrations. However, there is a Kp expression. When you see the P subscript, it is partial pressures of the components of the reaction. And it's written the same way, products over reactants, but the way you note it is you have partial pressure of CO, partial pressure of hydrogen divided by the partial pressure of methanol. So you would write partial pressure of CO and put it in parentheses like that, and then partial pressure of H2 and square it just like you did up here, and then divided by the partial pressure of CH3OH to the first power. So that's the expressions. Now those are not equal except under one certain condition. I'll show you in just a second. The relationship between Kp and Kc, we'll have problems on it and we'll work them, is Kp is equal to Kc, parenthesis, gas constant, R, temperature in Kelvin, to the delta N value. The delta N means the molar difference in molar volumes between the two reactants and products. We have 1, 2, 3 molar volumes on the product side here. Coefficients are moles, and that's also molar volumes. And then you have 1 molar volume on the reactant side. So your 3 minus 1 is 2, and that's what you would put as an exponent right there. Your gas constant is 0.08206. It's published on the reference sheet that is going to be attached to the exam, and the problem is going to give you a temperature, say 25 degrees Celsius is 298 Kelvin. So you would put 298 Kelvin, and it will more than likely give you a Kc value and ask you, well, what's the Kp? And so you apply it simply to this expression. And we're not going to worry about deriving it, just learn it. Now, of course, the reciprocal of that will give you Kc, and it's simply Kp to the minus delta N, RT and Kelvin, to the minus delta N value. So those are two equations that you can expect in the future in terms of writing whatever the numerical value is. Whatever the units come out, you don't care. But the numerical value is what you care about. Now there's one case in which Kp does equal Kc, and that's when the sum of molar volumes on the reactant side equals sum of molar volumes on the product side. For example, if I have the equation, let me get it up here, I'll show you. If I have the equation H2 gas plus I2 gas in equilibrium with 2HI as a gas, what's the relationship in that? What's the Kp-Kc relationship? Well, if you look at this, you have 1, 2 molar volumes over here. You remember molar volume is the volume occupied by 1 mole of any gas. Doesn't matter what the gas is or conditions, it's Vm. Now, if it's 0 degrees 1, you can say 22.4. Over here is a 2 coefficient, so you have 2 molar volumes. So the reactant molar volumes equal to the product molar volumes. So the change in moles or molar volumes is equal to 0. 2 minus 2 is 0. So if you want to write Kp equals Kc RT to the delta N, what would delta N be? 0. And so if that's the case, then this term goes to 1 and Kp equals Kc. So under the conditions of sum of the molar volumes of the reactants equal sum of the molar volumes of the products, then Kp equals Kc. And that's the unique condition. And here's your example there. And problems will come to you. Well, they'll give you, well, the Kp of this reaction, whatever it is such and such and such and such. Well, if you look at the reaction, you see the volume, molar volumes are equal, and it's also Kc, and then you work the problem in Kc expression, which would be molar concentrations, not partial pressures. So that's kind of a little twist in a problem that you'll see come up. I've got an example in the handout in there. Okay. This represents what we call the hydrogen sulfide scrubber reaction. In oil field, sometimes the wells get to producing hydrogen sulfide, and you need a way to control that. Hydrogen sulfide is a very deadly gas, and so they feed the gas into a carbon monoxide hydrogen combination with the methane and the hydrogen sulfide that comes out of the ground. Methane is part of the gas production. Anyway, those react together simultaneously and produce carbon disulfide and water, which is harmless, and the carbon sulfide is used in a lot of commercial applications. Well, to analyze this and find the K value for it, you have two reactions going on. One is the carbon monoxide reaction right here, which you introduced into the reaction chamber, and this is the one you're feeding into the reaction chamber from, say, the drilling operation right here. Well, to get the net reaction, you add the two together. And so when you do add reactions together, comes from Chem 1, you have carbon monoxide. Methanes will cancel out, as you see here. They're on opposite sides of the expression here. Then hydrogens will cancel out. Should cancel out here and water will cancel. Oh, it comes down. I'm sure I wrote that down right. I must have left out H2. I left out the H2 down here. I need a H2 on the end. Yeah, hydrogen gas should be in that collection also. Well, writing the equilibrium expression is what used the technique that I've shown you for the net reaction. So Kc would be products over reactants, just like we had explained earlier. So that's CS2 and H2O, water vapor, and H2, gas products, over reactants, CO and H2S squared. Now, what's the equilibrium number over here? Well, each one of these has a value already published and determined by some other methods. When you add two equations together, the equilibrium constant of the net reaction will be the product of K1 times, say, K2. You just multiply the two numbers together. That is, you would have 3.92 times 3.3 times 10 to the fourth. Like that. And you'll see this pop up in several problems as we get deeper into the chapters. And this comes out to be 1.3 times 10 to the fifth. So the reaction outcome is very efficient as a scrubber reaction for this application. So what do you need to remember? When reactions are added together, they give you, of course, a net reaction based on canceling and all of that. But the K values are the product of the two reactions added together. So multiply it, and that will give you the K value for the net reaction.